We are now looking at a teaching video on the application of differentiation, specifically on kinematics. We first look at part A, where we'll look at the symbols used in kinematics. And if you see the S there, it will represent displacement. And if you look at V represents velocity. And if you look at A, then it is acceleration. Now, all these three quantities are actually vector quantities. What it means is that all these items here would have a magnitude and a direction. So when we talk about magnitude, we are talking about, in this case, the distance. And direction, then we are talking about, in this particular case, how far is it from the fixed point. So you would expect, when we look at this quantity, because it's vector, that negative values are possible. Contrast velocity to speed. Speed is a scalar quantity. It can never be a zero. It can never be a negative value. But for velocity, if my travel towards this direction is positive, then the reverse direction will have to be negative. So, in short, for vector quantities such as displacement, velocity, and acceleration, there will be two portions to it, the magnitude and the direction. Now we look at part B. We want to focus on displacement. Well, displacement is displacement of a particle is measured from its origin to where it is. Now, the origin can be the fixed point that we talk about. Now, there are two cases here. So we talk about the case where there is no turning. So the particle starts from here when t is equal to 0 seconds, and it travels towards the right, and at this particular instance, t is equals to 2 seconds. So from t equal to 0 seconds to t equals to 2 seconds, there's no turning. So if I make s of x as the displacement function, describing the displacement of the particle from the origin, then the distance traveled will be equal to s bracket 2. So what I do is I'll take this time value, put it into the, I should put this as st, because s is in terms of t, time. Now I can also put it in another way. The distance traveled is equals to the displacement. So when I look at s of 2, what it means is the displacement from the origin to where the particle is at t equals to 2 seconds. Now we're looking at point B, no turning. That should be with turning. You can see the particle moves from the fixed point and then make a turn at t equals to 2 seconds and travel in the reverse direction towards the fixed point. Now, if S of t is the displacement function describing the displacement of the particle from the origin, then the distance traveled would be, first of all, the distance here, and then the distance traveled here. So this distance traveled from t equal to 0 seconds to 2 seconds can be found by simply doing this. Substitute t equals to 2 seconds into the displacement function. So that is the distance here. But I can take a times 2, meaning I have this distance plus this distance. Now I need to take away this particular part of the distance because the particle never traveled along there. So this distance can best be described by S bracket 3. That is the displacement of the particle from the origin at t equals to 3 seconds. So what I'll do is to take from 2 times of S bracket 2, S bracket 3. That will be the distance traveled by the particle. So you can see when the particle did turn, then I cannot just equate the distance traveled to the displacement of the particle. Instead, using a diagram like that mark the pathway of the travel, I can then decide what to do to find the distance traveled. As for this particular part, distance traveled not equal to, simply put, the displacement of the particle. You can see if I'm talking about distance traveled from t equals to 0 seconds to t equals to 3 seconds, and if I mistakenly take that distance traveled as S bracket 3, then it will be so wrong. Because you see, from this diagram, this distance is basically just a portion of what the particle has traveled. Now we look at common phrases. You see that if I have t seconds after passing through O, what it means is that when t is equal to 0 seconds, the displacement will be 0. So it means that at the initial part of it, at the start, the particle has to move off. So the displacement will still be a 0. Returning to its origin at t equals a second. So perhaps the particle has made a turn and now returning to the fixed point. So I would say the displacement, if I substitute the a into the t, then it will equal to a 0. Next, we look at the maximum displacement. Well, first of all, the first derivative will be v. But for the sake of sticking to displacement to illustrate the point, ds over dt, which is equals to the velocity, and I must equate to a 0. Now, I will use the second derivative of the displacement to decide whether it is a maximum displacement. So if it's going to be a maximum displacement, then I would have the value less than a 0. So you can see I put down here ds over dt as equals to v, that must be a 0 because we are talking about maximum point. The gradient should be a 0. The second derivative of the displacement, which is equals to the acceleration, is less than a 0. So for the minimum displacement, again, I'm talking about minimum point having 0 gradient. So it would be the same as the one before. And the second derivative, which is equals to the acceleration, must now has a value of more than a 0. So when we see phrases like that, we must have these phrases trigger off some ideas in our mind, and these are the ideas that we must have so that we can actually effectively solve the questions. We now look at velocity. Velocity is actually displacement differentiated with respect to t. And we look at some common phrases here. The initial velocity, that is velocity at t equals 0 seconds. So it's velocity at t equals 0 seconds. When we say a particle is instantaneously at rest, what it means is that the velocity is equals to 0 meter per second. So now we look at maximum velocity. So the first derivative of the velocity with respect to t must be equated to a 0, but that also is equal to the acceleration. Now, to determine whether the velocity is maximum or minimum, then I have to look at the second derivative of the velocity, and that has to be less than a 0. As for minimum velocity, I want to take the first derivative, which is also equals to the acceleration. It will be a 0 value because we are talking about stationary point, and stationary points have got 0 gradient. Then the second derivative will test out the nature of the point. So the second derivative of the velocity should be greater than 0. So when we see this, then we would have a minimum velocity at a certain instant. So if we are to find the minimum velocity, then we'll take the t value, the instance where the particle will experience minimum velocity, put that t value into the velocity function, then we have the minimum velocity. Now we look more into the detail of the travel of the particle. So if a particle turns in its travel, then velocity is equals to 0 meter per second. The sign of the velocity, when we talk about the sign, it means either positive or negative, changes after the particle turns. So in other words, if I start off from here at a fixed point O at t equals to, say, 0 seconds, then the particle turns at a certain time. Let it be 2 seconds, and here, at this instance, t is equals to 3 seconds. Well, if I say that the velocity is positive going this way, then the velocity returning to the origin would be a negative value. Or if that is going to be a negative value for velocity, then that will be a positive value. So there is a change in the sign. So another situation, or another way to see whether the particle has turned, first of all, we must obtain that v is equals to 0 meter per second. And you realize, using even the same diagram here, as the particle moves along towards this instance t equals to 2 seconds, the displacement is getting bigger. But after the turn, because it's returning to the fixed point, you find that the displacement is getting smaller and smaller because it's getting closer and closer to the fixed point. So what I would say here is that the displacement of the particle decreases. Decreases after the turn. So the most important thing is that when v equals to when v is equal to 0 meter per second, there is an indication that the particle may have turned. So we use such gauge, the sign of the velocity and the magnitude of the displacement, to determine whether the particle indeed has turned. We now look at acceleration. For acceleration, we have two different ways to describe it. One is basically just the second derivative of the displacement function with respect to t. The other will be the first derivative of the velocity function with respect to t. So this is just a very brief overview of the topic, and as you go into practices, you get to experience the full meaning of it. We come to an end of this video.